This is Dr. Ian Lundholm with How to Math, and today we're going to be working on an activity together. Alright, so it was my original plan to work these activities together with you live on Pronto. The sad state of things is that Pronto has been unreliable in terms of its ability to record videos, and there have been a lot fewer students that have been wanting to video chat with me than I initially expected. And so, for instance, I just had an activity on Friday with my linear algebra class, and it went fine. We made use of Jamboard, we made use of the Pronto chat at least, but exactly zero students wanted a video chat with me. And really, there was only one student that video chatted with me last week from your class. And so what I'm thinking is, it's probably going to be better for your learning if I record myself working through this activity and you make sure that you try to work through the activity first. But then when you get stuck, you can use this to help you get unstuck. But I do think it's beneficial for you to try and wrestle with things first. So yeah, use this if you can. I'll try to do a good job on this activity. Honestly, I haven't done it in 2 years, so it's going to be a little bit of an exercise here. All right, let's see what we got. Activity 8, put my name on the paper. Great. The integral test. We have a series, and it's connect the dots function, the restriction, the infinite series. The improper integral converge or diverge together. Yay. In this picture, the red area is simultaneously the right-hand Riemann sum and not that infinite series, it's just a series that goes up to 5. Okay, cool. Part A, check. As long as the function is continuous, positive, and decreasing as x goes to infinity, the right-hand Riemann sum will be smaller than the integral, and the left-hand Riemann sum would be bigger than the integral. But they would all converge or diverge together. That makes sense. Since series match up so nicely with Riemann sums, we can use integrals to test whether series diverge or converge. Okay. Again, check. Part C, prove that the sum converges using an integral test. Is the series bigger or smaller than the integral you used? Okay, so that's literally the same thing that we see up here. And so all we have to do is work with the same integral. We're working with the improper integral from 1 to infinity of 1 over x squared dx. Yeah, if we're going to do this properly, we write it as a limit. Then we take the antiderivative. Let's do this. We've got negative 1 over x for this one. We add 1 to the exponent and then divide by that exponent, and then the exponent was negative 1. All right, and then we've got this. Let's bring it up here. Limit as b goes to infinity of, basically negative 1 over b plus 1. And this limit b goes to infinity. It just goes to 1 overall. So that's really using the integral test. The series is smaller than the integral that I just found. But yeah. Hope that's right. Why doesn't the integral test apply to the following series? Look at part B above. Do you still think it would converge? Why? Try to graph on Desmos if you'd like. Okay. Or GeoGebra. Okay, we've got this infinite sum, and it's cosine on top instead of 1. The reason that this is not guaranteed to converge by the integral test is that while this function would be continuous, it's not necessarily going to be positive and always decreasing as x approaches infinity. Well, in this case, n approaches infinity, but yeah. The function that goes along with this would be, cosine of x over x squared. And yeah, we could try to plot that. Honestly, well, all right, I'm gonna try real quick. Let's go to GeoGebra. We're going to need to use the sequence function. Let's do this one. The expression I would like to plot is a point. I would like to plot a point where the x value is just n, and the y value is the cosine of n divided by n squared. Shoot. Come on, dude. There we go. Boom, n squared. All right, so that should give us a series of points. And if we put our variable in as n, let's start it at 1, and we'll end at 20. All right, but yeah. This is what the terms of that series would look like. You can tell that, yeah, they're not always going to be positive. They're not always going to be strictly decreasing because the cosine function, wiggles up and down. So that's what that looks like, and that's why the integral test doesn't necessarily apply. So, not decreasing and positive. I do still think it would converge. Mainly, I guess my best reasoning would be using the squeeze theorem to say, hey, this would be bounded above by 1 over n squared. And it would be bounded below by this, right? And so really this sum is in between 1 and -1. Whoa. Yeah, squeeze theorem. Cool. Moving along. Find the sum of this series. It's telescoping. All right. Yeah, we have this quadratic function on the bottom, and I believe that we should use partial fractions here to decompose this thing. So, yeah, we've got 3 over n squared plus 5n plus 6. That's the same thing as 3 over n plus 2 and n plus 3. And we could use a little heaviside cover up here. If n equals -2, then that entire fraction, if we cover up the n plus 2 part, would be 3 over 1. So it's just 3. So 3 will go over n plus 2. 3 over n plus 2. And if n equals -3, then that part would be 0 and gets covered up. And yeah, -3 plus 2 becomes -1. So you'd have 3 over -1, which is -3. So you'd have -3 over n plus 3. Yeah. And so we could write out, say, the first few terms of this to make sense of what's going on. We would have 3 over 1 plus 2, which is 3, minus 3 over 1 plus 4, which is 3/4, plus 3/4 minus 3/5, plus 3/5 minus 3/6, so on and so forth. Until, I mean, you end up getting something that looks like 3 over, you know, I don't know, n and minus 3 over n plus 1. And this is telescoping because all of these pairs of middle terms cancel out. These ones cancel, this one cancels out. And so that all we're left with in the end is basically 1 minus something that is approaching 0. And so again, the sum here actually would just be 1 in the end. So that's just a little partial fractions. Okay, here are the tougher ones. Determine whether the following series converge or diverge. If it diverges, find the sum. Actually, these look pretty familiar. Are these from the book? They are from the book, I'm pretty sure. Let's see. Anyways, let's pretend that they're not from the book and just try to work them from what we know. I'm getting strong geometric series vibes from this first one. because we got 2 to the n and 4 to the n minus 1. And in order to make sense of this, I think teasing it apart a little bit would be beneficial. So let's see. We got the sum, n equals 1 to infinity. Two times 2 to the n minus 1 over 4 to the n minus 1 minus 3. We could split that up into two different things. Here we would have 2 times 1/2 to the n minus 1. We're just taking that here. And, you know, this 2 is the one that shows up out front here. And then minus 3 times n equals 1 to infinity of basically 1/4 to the n minus 1. Where, you know, that's coming from this part. Okay, and now we could use, now we've got two perfectly good geometric sequences, or geometric series, that we could use our formula for. So we've got 2 times, I think it's A, so like the first term in the sequence over 1 minus R. As your teacher, I really should know that. Let's see. Yay, okay. I just looked it up. That's correct. So I'll do that there, and we'll do the same thing over here for whatever this A and this R are here. I'll give them some subscripts so that we know that they are two different starting points and two different ratios between successive terms. Okay, we can do this. 2. The first term in this sequence, or that series, would be inserting a 1 in there. And so we would have 1/2 to the 0 power. That would be 1 times 2 would be 2. Or actually, don't multiply it by 2 because that 2 is already hanging out front. So it should just be 1 on the top. And then, yeah, the constant ratio is 1/2. So we subtract 1/2. No big deal there. Here, again, the first term would be 1. And the constant ratio is 1/4. Okay. So on the bottom here, we have 1 minus 1/2, which is 1/2. And so we've got 2 times 1 divided by 1/2, or 2 here. So that's 4. And then down here, we've got 3 times 1 over 3/4, which is really 4/3. And so you end up doing 4 minus 4 and getting 0 in the end here. This totally is from the stinking examples that we went through on Thursday. All right, well, sorry if this is just a repeat, you guys, but hopefully you are trying this ahead of time and you are getting a feel for whether you really remembered those things, whether you've internalized this a little bit. And here again, we have this sum. We want to see if it converges or diverges. This one looks a little bit more like we're going to need to do partial fractions to tease it apart and see what we've got. Just looking at this, if I were to multiply that and use the distributive property, we would have n squared plus n. And yeah, I'll be honest, I'm a little bit concerned about whether this one's actually going to converge, because this ratio that we have in front between the, the dominant powers in the numerator and denominator, the degree of the numerator and the denominator, that ratio is very similar to 1 over n, which is the harmonic series, which diverges. So I think we're going to try to do this justice and try to, see if this telescopes or whatever, we're going to actually do the partial fractions. But my gut reaction is that this is going to diverge. So yeah, partial fractions, let's just go ahead and break it up. I'll try to talk you through the cover up. So the first thing that we'd sub in for cover up is 0 for n. And that would be 2 over 1. So 2 goes over n. And then the other part would be n plus 1 on the bottom, where we'd be substituting in negative 1. And so we'd have negative 1 plus 2 on top, which is 1, and negative 1 on the bottom. So we'd just have negative 1 here. Yeah, and again, I think that this is a problem that we've done recently. What I could do with this is, the easiest way to see that it diverges is splitting up 2 over n into 2 copies of the harmonic series. And then we have this one, which is just the harmonic series indexed 1 off. This part over here telescopes, and it goes to 1, because you can see that the first term there would be 1 over 1, and the tail of it would just fade off. So this part is a telescoping series that would approach 1, and the other part is a harmonic series, which diverges. So we've got something that diverges plus something that is finite, and so the overall series diverges here. Yeah, all right. Well, I'm sorry. That activity was a little bit of a letdown in terms of its novelty, but it was kind of good as a check of understanding of whether we actually, understood what's going on so far in this chapter. As long as you tried it yourself first. Okay. Again, I do mean this whole, recording of an activity thing to be beneficial for your learning. I'm not trying to get out of meeting with you, but really I'm just hoping to help you learn. And especially since people have not been wanting to video chat with me, I thought that this would probably be, the best way to help you learn at your own pace. All right. Well, see you guys this afternoon. Hopefully this will be helpful.